Hi students, Professor Nugent here. Let's review hypothesis testing. Recall that when we construct hypotheses to test the value of a coefficient or the mean of a sample, we write down two hypotheses. We have a null hypothesis and an alternative hypothesis. The two hypotheses are mutually exclusive and collectively exhaustive. That means the two hypotheses together describe, so they're collectively exhaustive, they describe all of the possible values that coefficient can take, and they're mutually exclusive, so there is no overlap between the two hypotheses. All right, so that means that either one or the other is true. They cannot both be true. And what we want to try to do is try to prove that the null hypothesis is false, and if we can prove that the null hypothesis is false, then that's good evidence that the alternative is true. All right, and that framework comes from the fact that these hypotheses are mutually exclusive and collectively exhaustive. The setup here is typically that we want to construct the null as being like the status quo. That's what we want to try to prove false. So if we want to test whether a coefficient is greater than 1, then the null is going to say, well, the coefficient is less than or equal to 1. And we're going to try and prove that the coefficient is not less than or equal to 1 so that we have evidence that it is actually greater than 1. So let's look at the three different kinds of hypotheses, the left tail, right tail, two tail, so that you have a more concrete example of what I mean. Let's look at first a left-tailed test. For a left-tailed test, this may occur if you want to test whether, or you suspect that, let's say you're testing a coefficient is less than 1. All right, we want to test that a coefficient is less than 1. So then the null hypothesis is going to be that theta is greater than or equal to 1. And the alternative is that theta is less than 1. We want to try to prove that the coefficient is not greater than or equal to 1 so that we have evidence that the coefficient is less than 1. Now let's plot these hypotheses on a distribution. Let's assume that we can plot the hypotheses on a normal distribution. This is a left-tailed test, and let's use a level of significance of 5%. So the null hypothesis is going to be true in this part of the distribution. And then this part of the distribution is what we call the rejection region. This is alpha, is 0.05. This would define your critical value. If this is normally distributed, this is negative 1.645. what we want to see is that the test statistic is sufficiently far from 1, sufficiently below 1, so much so that we can reject beta being greater than or equal to 1. Okay. And let's review the test statistic, the t-stat. That's going to be the estimated value minus the null hypothesized value over the standard error. All right. So if this test statistic shows that the estimated value is so far below 1 that the null hypothesis can't be true, then we can reject that thing. And that's what we want to be able to show. All right. So then let's look at a right-tailed test. We're going to test that the coefficient is greater than 1. So the alternative is that beta is greater than 1, null. What we want to try to prove false, that beta is less than or equal to 1. Alpha stays the same, test statistic stays the same, but the rejection region is now on the right-hand side. All right, here's the rejection region. This is where the null hypothesis is true. And so what we want to try to do here is show with our test statistic that the difference between beta and 1 is so large, so it's so high up on this distribution, the difference between beta and 1 is so large that the null hypothesis can't possibly be true. Right? So think about what this test statistic means. This is the number of standardized deviations. So we want to show that the number of standardized deviations is so large that this null hypothesis can't possibly be true, because the difference between the estimated value of beta and 1 is so large that the null hypothesis can possibly be true that beta is less than or equal to 1. So that we reject the null hypothesis in favor of the alternative. Finally, let's look at a two-tailed test. So we want to test whether a coefficient is equal to 1. And in this case, the null hypothesis is going to be that beta equals 1. The alternative is going to be that beta does not equal 1. And here, so we'll still have a 5% level of significance, but the rejection regions are split up into two tails. The rejection region is alpha over 2 in the left and right hand side. So this is 0.025, and the critical value is plus or minus 1.96. The t-stat is the same. The test statistic is estimated value of beta minus the null hypothesized value of beta over the standard error. And what we want to show is that we're going to try to prove the null hypothesis false, proving that the difference between the estimated value of beta and the null hypothesized value of beta is so large that the null hypothesis can't be true. And if the difference is not so large that the null hypothesis can't be rejected, then the difference between the estimated value of beta and 1 is statistically insignificant. All right, so this is the region where the null hypothesis is true. Okay, folks, so this has been a very brief review of hypothesis testing. If you have follow-up questions, please send me an email.